relativistic dynamics in detail in the talk. So, not shifting. You have to use this page up, page down. Okay, sorry. Yeah, so I'm going to cover this ground. First, I'll talk about homoclinic orbits, which are important for this for these events. Then I'll talk about tidal disruption statistics, how it can be used to build mass functions, a little bit about relativistic loss cone theory, MD rates, and future directions. You can see that there are aspects of this talk which are important in terms of relativity, because there are relativistic corrections which make changes to the predictions made earlier using non-relativistic calculations, and of course the detection of gravitational waves and MD rates for extreme mass ratio and spirals. And so we will just talk a little bit about the Kerr metric and how the dynamics changes. There's a paper which with my student, Prerna Rana, we looked at eccentric orbits, spherical orbits, and non-equatorial separatrix orbits.
We are not able to hear it. So maybe I will just try to increase the volume.
Am I audible now?
Think so.
Okay. Is it better? Okay, thank you. But this thing doesn't go away anyway. We'll have to live with that. I'm sorry about it. So what's important is that there are different classifications of orbits. Particularly, we looked at bound orbits and what are the conditions for bound orbits. And the one in the middle is a spherical orbit, orbits on a sphere, and then one on the left is a non-equatorial eccentric trajectory. And on the right is a separatrix trajectory, which is also called homoclinic, which is of great importance for gravitational wave radiation scenarios. So this problem can be solved exactly, and there are 4 routes for the effective potential. So when you proceed ahead, there are different regions that's described in the paper, how to calculate those 4 routes and what are the different. So we did an analysis of this, trying to classify the orbits using this E and L classification scheme, which has been done earlier. But the useful thing we found was when you translate it to a new set of coordinates, that is E and mu is the inverse lattice rectum, the analytics become easier, and then you are able to translate this into a space of mu and E, where things look a lot simpler. I'll explain that in a minute. So, and even in these coordinates, the integrals of motion are easy to evaluate. So we did that, and then you get elliptic functions, not surprisingly. But these are a little bit more manageable for various reasons, as we shall see. So, so this is the region I was talking about, mu and E. And this mu is inverse lattice rectum, which is basically the same sort of parameterization which is used for Kepler, solving the Kepler problem. That is 1 over r equal to mu into 1 plus E cos chi, where chi is the ordinate of motion. And in if you want to keep the integrals real, there is one index n in the elliptic functions. So if that has to be less than 1, you get this condition, which is a condition for bound orbits. And there's another condition that says the periastron point is outside the horizon to make it more astrophysically meaningful. And you can do various things. So let's look at this particular diagram, mu and E, where there are 2 points. One is a stable point and one is the marginally stable point. And there's a red line that runs across. Now, the solution for the red line in these coordinates is a 12th order polynomial. And for the spherical case, it's a 9th order, and M is an 8th order. So you can actually work out these things in some detail. And that's, in fact, one of the novel results that comes out in this paper. And clearly, things are easy to evaluate. So what do you do with these? And this is one of the results which was published in AppJ by us, which is an analog of the Bardeen's classical result for 2 dimensions. So what is the separatrix curve? So you see on the left, this is the innermost stable spherical orbit, because we're doing this in 3 dimensions, where all the 3 roots, the 3 roots are equal to each other, and the 4th root is inside. This, now here, what happens, you have R1 at infinity, and then you have R2 equals R3. So this is what happens for marginally bound stable orbit. So what happens for these separatrix trajectories? That's the red line. Any one of those orbits has a very peculiar situation where you have an orbit that comes in from infinity and then it spirals around in the torus. And this is an important trajectory because in the study of spiraling bodies, the gravitational wave emitting has to go through this particular phase. So the separatrix point, locating the separatrix point is important. So hence the solution for this, which we found using these coordinate systems is quite useful. It was previously done in 2 dimensions. Now it has been done for 3 dimensions. Okay, so the subsequent to our paper, there was a solution for this in 12th order, but we found another solution in 9th order. It's a matter of detail, but it helps us to calculate the inner ISSO, the marginally bound spherical orbits, separatrix orbit. There are taxonomy formulae, light sphere, etc., which is so advantageous when you move to this new set of coordinates. The other things that we looked at are zoom ball behavior, and so this is in an upcoming paper. So we can actually use this advantageously by calculating an adiabatic evolution through periodic orbits. And clearly it has computational advantages. So the summary of this first part is that we find a simplest possible solution for a non-equatorial separatrix orbits. And so this is an advancement over previous work. And there's a remaining cubic factor which comes out, which can be investigated and has probably connections to the light shadow problem. So the conclusion here is the homoclonic clinic orbits offer the kind of crucial signpost that demarcates physically distinct regions of conservative and inspiral dynamics, and bound from plunging, whirling from non-whirling, smooth and chaotic. So these dynamics are important, and I'll show you how we have exploited them in studies of tidal disruption events, for example. So why are TDEs important? If you have active galaxies, they're high luminosity, they have jets. Quiescent ones are quiet. So they are particularly interesting cases where you can see stars being disrupted. And these events are now beginning to be observed. And so we can learn a lot about it's a good laboratory to do black hole astrophysics. You can test stellar models, you can calculate the observational signature. So a lot of gas dynamical physics that can be tested. So, and also it's a laboratory for creating jets. So if you look at the TD catalog that we studied, this is a paper by me and Mageshwaran, and we looked at the statistics of these objects. So the statistics of these black holes is also very important. Number of distribution of black holes in redshift and in density. So this gives us clues about the cosmic density of black holes and also the cosmic history, cosmology itself through these studies. So what we did was we looked at the existing data. We tried to derive the parameters of the mass and redshift and also the spin of these objects and build the statistics. And here's using our model, 2 models, which for sub-Eddington and super Eddington, which was published last year, we were able to extract these parameters. So with that, we calculated also the TD capture rate. This is an earlier paper. And knowing the TD capture rate as a function of mass, angular momentum, etc., we can actually calculate how the capture rate of stars around black holes. So here is an example of how the capture rate depends on mass to the power of minus 0.23. So this is in the details of the luminosity and how the accretion affects it. There's cadence. There's the survey parameters. Using that, we can calculate the expected number of events that you would see in the entire sky. So to do that, first you need to build a mass function. So we take the Schechter function and then use that to make the galaxy as a function of mass, galaxy using two relations, the Faber-Jackson law and the M-sigma relation. So then you write the number density of black holes that are distributed in mass, and then each galaxy has a certain occupation fraction. That is, each galaxy, there's a fraction of them are occupied with black holes, and that's an empirical formula given here. So we use that, and then calculate the detection rate that each survey would pick up, depending on the flux limits of the survey, the fraction of the sky covered, the cadence, etc., etc. So that turns out to be an integral over cosmic volume, and then you do this integrals over redshift, mass, stars, etc., etc. So then you are able to take in the input the detector parameters for various surveys, the 6 surveys, and then you come up with a likelihood function of the detections that are expected versus detections that are observed. With that, now you're able to maximize the likelihood and then extract the parameters of the Schechter parameters, as well as a scaling parameter which was related to the occupation fraction. So these are the expected parameters, which is roughly in the range, and this is the results of the likelihood. And these are the results of the Schechter galaxy mass that we discovered, we found, and these are roughly in order of the existing galaxy mass, Schechter mass, parameters that are found out in literature. So with this, you now know the Schechter parameters. You can now calculate the TD black hole mass distribution. That is the number of black holes which are participating in TDs. So that depends on the activity. So if there's an activity of the fraction which has to be included over and above the occupation fraction. So that is called a duty cycle. And then once you correct it for duty cycle, the black line here corresponds to the TD function, the function of the mass function of TDs, which is inferred from the galaxy distribution. And the red and the blue lines are the galaxy distributions, and then a fraction of the TDs. So you can see there's a difference. We go ahead and use the activity correction. You correct it for activity. And when you do that, you can see that the two lines roughly match, but there's a divergence at the higher mass end. And you see that it doesn't match there because, and the reason for this, why there's a mismatch at higher mass is because of nuclear activity in the black hole mass function. And I'll explain that in a moment. We do galaxy averaged capture rates, and the capture rates are now in sort of more in line with what's this observed, what is observed. So the statistical average do match the observed rates. Previously, there was a tension of a factor of 100 or so. Now that has been reduced using relativistic corrections and as well as doing a galaxy average. So the conclusion of this part is that the TDs are dominated by low mass supermassive black hole. They are not they're not observed for higher mass black holes, and this is the difference may be attributed to occupation fraction, duty cycle, and relativistic effects. So as you go to higher mass black holes, we have to use relativistic effects which have to be included, and then you can make the rates match. Coming back to the relativistic dynamics, as I mentioned to you, the MBSO is very important, and that gives you a measure of the capture radius. So there are important radii, which is the capture radius, then there is a pericenter, and the horizon, of course, and the tidal radius. So the tidal radius is so you try to compare the tidal radius, the pericenter, as well as the capture radius. So these different radii, when they're at different magnitudes, they make a difference to the dynamics, and I'll explain to you how. All right. So how do you calculate the tidal radius? You take the second differential of the effective potential, then you're able to calculate this, a sixth order equation. And once you calculate the tidal radius, you can do that as a function of mass. You can see there's a difference how it changes as a function of mass. And there's clearly a difference also based on the density of the star that's involved. If it's a white dwarf or a regular star, obviously the tidal radius is going to be different. So on the left, the main sequence goes through a drastic change at the critical radius and critical mass, and then there's a steady decline in the case of white dwarfs, which clearly is because there is a point where the tidal radius becomes very close to the horizon.
You have 9 minutes left.
Okay, thank you. So these tidal radii can be now calculated as a function of density and angular momentum. So these are important functions. Once you have this tidal radius as a function of angular momentum and also as a function of orbital angular momentum and spin, then you can look for a sort of condition for disruption or capture. So a tidal disruption event is possible. For example, if the pericenter, which is xp, is less than the tidal radius xt. So if it reaches xt, the xp is less than xt, so it gets disrupted before it reaches the pericenter, and the capture radius is further inside. So this is one condition for clearly this is a condition for tidal disruption. With this, you can find the critical mass. So you can find the density such that this condition is satisfied, and you can do that for main sequence, white dwarf, and neutron stars. What is the condition for disruption or capture? So if, for example, the capture radius is less than the tidal radius, which is less than the pericenter, right? So it won't be tidally disrupted. Right, it will follow the orbit and is neither getting captured nor disrupted because the capture radius is further inside. So it will get neither captured nor disrupted. So again, the stars can get tidally disrupted if the pericenter is less than the tidal radius or the capture radius. So all these things are summarized, these different conditions for disruption or capture, tidal disruption of stars, star capture without disruption. And detection of events where the star gets disrupted, but inside the capture radius is unlikely because the debris will plunge into the black hole. There's another case where the star is consumed without disruption, and this is a case for MDs. So these different 5 cases can be studied when you take the XT, XP, and XH and XC in relation to each other. So the result, for example, is a density angular momentum diagram. And the dashed area shows the various cases where there is a stellar capture without disruption. And in the solid area, you will have stellar capture with disruption. So if you're interested in a main sequence star, you will probably follow that, find out which area you are, and then whether it's going to get disrupted or captured without disruption, various kinds of issues. So, and of course, there are more discussions of how to find this whole argument can be turned around to ask, is there a dependence that can be created on the mass? So there is a critical black hole mass below which it will get, it will get disrupted, and above which it won't get disrupted. You can do that for different kinds of densities, etc. So these are some calculations. And of course, the result of this tidal radius and the minimum angular momentum has a direct impact on the loss cone radius. Loss cone radius is a radius for capture of black holes when of the star by black holes in its orbit. Okay. So you can calculate this, and this will of course have a dependence on the number of stars getting captured as a whole. And this is one of the results that we found, that if you do these calculations, put in the Fokker-Planck and calculate the diffusion of stars, and finally how many get through the lost cone and into the black hole, you find that the rates are fairly, interesting, in the sense that if it's relativistic corrections, then you're within the observed regime, and there's also a peak, as a function of mass. After a certain higher mass, it drops off significantly. So this is an important clue which for formation of black holes. If you have a star cluster, then with masses of order 100 or so, then you can have a high rate of accumulation of mass. If you have a black hole mass of 100 solar mass or so, the n dot is pretty high. Then it falls off very sharply for higher black hole mass. This is a comment by one of the Nobel Prize winners. Why don't we see emission from matter and falling on black hole? And why is it not so high? And it's partially answered by these two calculations. If you do it non-relativistically, you get a higher value. And if you do it relativistically, you will see a much lower value, more in line with what is seen in observations. And we also did the electromagnetic signatures of these tidal disruption, and this is, you can see that we're able to match the curves.
4 minutes.
Now, okay, so did I hear you right? 5 minutes or so?
4.5.
Okay, fine. So I hope you accounted for some of the.
Yeah, I did.
Yeah, okay, thank you. Yeah, so now when you now ask the question about MVs, so you have extreme mass ratio in spiral. What happens when it's not disrupted and it goes into this, you have a strain which can be calculated, and then a probability of detection which follows the same sort of arguments. And then you have a mass function, and then you integrate and then get the signal. So this is the parameters for the calculation for main sequence and white dwarfs. What is the fraction of stars which are in main sequence? What is the fraction of stars which are in white dwarfs? What are the mass limits, low and high? So you do all these calculations, and then you find out the rates, and there are few detection rates are of the order of a few hundreds as a function of redshifts per year, right? So this is a prediction for LISA mission. And so the conclusion of this part is that the stellar feeding rate on the black hole depends on the power law index of the stellar density. And the occurrence rates for different candidates, for main sequence, for white dwarfs, etc., are given here. And for different mass limits, it has been calculated. And of course, we can improve this by making more improved calculations, and it sort of matches with some other predictions in the literature. So I get to the diagram which I began with, of trying to tell you what is the end game of stars in the galactic nuclei. Either you get MREs or you get TDEs. What is the source of most TDEs? Source of most TDEs are objects which are very far away, right? So this, you can see that the pericenter is as a function of RS, and then the distance is a function of RS. So they're coming from very far away, nearly radial orbits, and they come in and they hit this line, which is the time for gravitational wave is roughly 2-body time, and that describes one radius. And then they hit the tidal radius, which is a horizontal line that you see. So that's the TDEs. And then you have MREs, which have got circularized because of the sufficient time for TGW to operate, and then they become circular, and then they emit gravitational waves and become MREs. So these are the two regimes which are the end games of this scenario. And clearly, the details of these end games requires a lot of technology which we have developed. I told you about the relative positions of the capture radius, the tidal radius, and the horizon, and also tidal radius, horizon, capture radius, pericenter. So all these things play an important role in selecting whether the object ends up as a TDE or MD, right? So this is a diagram, sort of a thought experiment in 2019 paper. But the details of all this and the division of MDs into TDEs, what is the fraction, all that depends on the details that I just described to you. So it's a clearly important step for us to take to examine the dynamics in stellar clusters. To using a fully relativistic model, we can calculate conditions for both events, TDs or MREs, and we have the technology to look at the light curves developed for electromagnetic emission. We have also developed rates for gravitational wave scenarios, occurrence rates. So with all these properties of occurrence rates and also to build cosmic density models, so these are kind of useful things that can be built out of TDs and also MREs. If you have a good statistical model and you have enough sufficient data, we can probe various important models about black hole mass functions, about the physics of TDs, dynamical rates, etc., etc. So I'd just like to end with this. Thank you very much.
Thank you, Arun, for keeping to the time. So let's start with questions. Are there any questions in the room or in the online audience? I cannot see things in the room. So Arun, can you please take them? And
yeah, there is one hand raised. To
yeah,
yeah,
go ahead.
Yeah.
It is about the last point on your conclusion or summary slide. What are the event rates estimated for EVSA for MREs?
Oh, it's a few hundred per year to few thousand. Okay, depending on whether you're talking about neutron stars, white dwarfs, or the height. Yeah. But as I said, that part, because we have done a little bit more work recently on the locations, on the capture radius and all that. So the sophisticated calculations are yet to be included. So that's a part of this new paper that we are working on. But the other one was done using non-relativistic, I mean, relativistic, but not as sophisticated as this.
Thanks.
I can see a question by Samik Mitra. I'm going to ask him to unmute in the from the online audience. So
am
Samik,
I audible?
Yeah, we can hear you. Go ahead.
Okay. So I have a brief questions about the angular momentum profile when TD is happening. What kind of things for the angular momentum we will see? I mean, how different it is from the accretion profile?
Okay. Look, we are at this point, when I said angular momentum, I'm talking about the orbital angular momentum of the star, right? So
yes.
There is a relationship. In fact, you can look at the paper published last year between, with Mageshwaran and myself, where we calculate the gas dynamical angular momentum in the disk in relation to the angular momentum of the incoming star, right? So that is a little bit of a complicated expression. But in fact, I may have that expression here, but I don't want to get into that at the moment. But when I was talking about angular momentum, I was talking about the angular momentum of the star, which is coming from the stellar density around the black hole, which is a roughly a Hot distribution F of E, and roughly the angular momentum is kind of not it's not an FEL kind of thing; it's an F of E distribution. So there's all kinds of range of angular momentum possible. So you will have radial orbits, you will have circular orbits, you will have all kinds of orbits. So there is no specific, there would be a cutoff in angular momentum in terms of capture, right? So if it's lower than the capture angular momentum, it will just plunge into the black hole. But other than that, the distribution should be quite straightforward, flat.
And it is always remaining sub-Keplerian in nature, right?
Okay, now see, what happens is, even if you're not in a plunge trajectory, or if you're not in a radially, if you're not in a situation where you will be captured, what happens is that there is a loss cone. And if you remember, loss cone is a region where it will, by several gravitational two-body encounters, your angular momentum may get pushed into a situation where you fall into the black. So it's a loss cone in phase space. So that is the calculation which involves solving the Fokker-Planck, and which is a sort of a hole in phase space. So as the stars are getting kicked around because of collisions, then you can get the loss cone filled. And that is what is the calculation which I talked about, which is n dot, which is the number of stars being captured. And that depends on how the loss cone gets populated by stars falling in to the loss cone by getting kicked around. So that is friction, right? Dynamical friction or encounters, stellar encounters, etc. And that turns out to be, that rate turns out to be roughly 10⁻⁻⁶ per year per galaxy.
Okay. Okay, sir. Thank you.
Thank you. Thanks, Arun. Maybe the next speaker can set up and we can check if there are more questions. I don't see any in the online participation group. If not, then is the next speaker around?
Okay, thank you very much.
Thank you. Thanks, Arun. Yeah, you can use the reactions online, participants. Okay, so the next speaker is Basundhara Ghosh. She will tell us about intrinsic and extrinsic correlations of galaxy shapes and sizes in weak lensing data and flexions.
Hello, am I audible? It's fine.
Yeah, we can hear you.
Okay. Hi everyone, my name is Basundhara and I work in ISC Bangalore as an DST Inspired Faculty Fellow. So the title of my talk is Intrinsic and Extrinsic Correlations of Galaxy Shapes and Sizes in Weak Lensing Data and Gravitational Flexions. I'm sorry for the extremely long title, but the talk will be on time, I assure of that. So just to give you an overview of what weak gravitational lensing is, because that's the background of the discussion, although it's probably known to most of you. But so essentially what happens is that when we are observing some source from Earth using our telescopes and instruments, we know that we are able to observe certain sources because photons are traveling from them to the observer on Earth. But it's not so straightforward because the photons undergo deflection along their path due to the matter distribution that is present between the source and the observer. So this deflection of photons is manifested in the form of weak gravitational lensing. And observationally, how we can account for that is through a change in shape or size, simply put. So if we have like a circular source image given by this blue circle, this simple cartoon diagram that you can see here. One thing that can happen is either there is a change in size of the source image, so you can look at it, look at a magnification of the source image in terms of this red dashed line, red dashed circle that is there, or there can be a change in shape or an anisotropic stretching of the source image. So it could manifest in form of this dotted green ellipse kind of structure. So quantitatively, the first thing we call it as the convergence, and the second thing we call it as the shear. And the convergence is simply the Laplacian of this quantity, which is called the lensing potential, which is a function of the deflection angle that the photons undergo. And the other thing that is the shear, it is a complex quantity and it is made up of two components, gamma 1 and gamma 2, which are also related in terms of second order derivatives of the lensing potential. But why is lensing important, or why do we use lensing signals as cosmological probes? Is because observationally cosmic shear is a very important quantity because it allows for a statistical analysis of the properties of the matter distribution at different epochs, because light is coming through different epochs. So if you study lensing and how it affects the shape and size of images, you can kind of have an idea of what kind of spatial geometry the universe has. So it is a powerful cosmological probe. But despite weak lensing being such a powerful probe, it is disturbed by certain contaminants, one of which is the intrinsic alignment, which is an astrophysical effect, a local effect. which causes galaxies to have the same kind of effect that lensing causes. So you also observe change in shapes and size of galaxy images due to intrinsic alignments, but this is not exactly the weak lensing signal. So this is kind of an additional effect on the weak lensing signal. So we need to see how strong it is and how it is affecting our measurements so that we can have an unbiased information from the cosmological probes. So we need to understand the intrinsic alignment signal and be able to separate it from the cosmic shear. And if we can separate it, it's not that it's completely a contaminant. We can also have some information about the respective environments of galaxies from intrinsic alignment signals, because these are local effects, and this is what I'll explain in the next slide. So when I say intrinsic alignments are local effects, this is what I actually mean. So if you look at this very simple diagram, especially focus on the lower panel. So as I said, lensing is caused when photons are passing through a dark matter distribution and getting reflected. Now, if we have galaxies close to the dark matter distribution, as you can see here, the blue ellipse, they undergo some tidal distortion, or they are in the vicinity of tidal forces that arise due to the presence of the dark matter distribution. So that will cause a certain kind of alignment of the galaxies in close proximity to the dark matter distribution in comparison to this red ellipse, which is far away from this concerned dark matter distribution, which is undergoing the usual lensing effect. So this has this convergence and shear thing going on. And the blue one is getting aligned in a certain way because the tidal forces exerted by the dark matter distribution is causing it to get aligned. So in our work, so I'll very briefly summarize two papers that we have worked on together with collaborators from University of Heidelberg, Germany. So the first question we want to ask is, so we are saying that there are certain kind of shape and size change being caused by intrinsic alignment as well as weak lensing. So we want to see how they're correlated with each other, and how significant is their contribution and how we can measure them, like what is the signal to noise ratio. That is the main question. The other thing is, if we extend our model to a higher order, that is called the flexion. So by extrinsic I mean lensing, and intrinsic I mean intrinsic alignments. So what is the contribution of even higher order contributions of this tidal shear? That is the question. So in order to answer that, first we need to understand that there are some analogies and differences between lensing and intrinsic alignment that are very interesting. For example, in case of lensing, the relevant quantity is this gravitational potential in units of c square, and in case of intrinsic alignments, we look at the velocity dispersion sigma square. And in the case of shear, the lensing shear, the gravitational tidal field is integrated along the line of sight, as I showed you in the previous diagram, that the concerned galaxy needs to be far away from the dark matter distribution. And in case of intrinsic alignment, it is due to the local gravitational tidal field. And the kind of alignment is also different. So lensing will generate a tangential alignment, and in case of intrinsic alignments, they align with the radially with the large structure of the dark matter distribution. So this is just for it's fun information. But if we go to one order higher, so shear and convergence is essentially when you take like a second order Taylor expansion of the tidal shear. But if you go to one order higher, that is, if you look at third order lensing, you will see there are additional effects causing. So when we consider that shear and convergence themselves have a gradient, they are not constant. So we have something called flexion. So this is a simple unlensed picture. This is slightly magnified. It's not very clear here, but it is actually. Then the shear is a change in shape that I mentioned. And these flexions, which are like spin 1 and spin 3 quantities, these F and G quantities, they are order higher, and they are like gradients of the shear and convergence. So this is an additional effect. So what we do is to, as I said, we expand the tidal shear in case of shape size, we go to the second order. So I won't go into the details of this because of lack of time. But we are going another order higher in case of flexion, essentially. And then we have like the Pauli matrices as basis here, and like we have other combinations of Pauli matrices here as basis in case of flexion. And what we can compute here is the change in size, the change in shape here. And in case of intrinsic flexion, we have the gradient in size and gradient in shape. So it's like, there is a change with respect to time. So it is what we are looking here essentially is a tidal effect on a virialized self-gravitating and spherical system. So when you have a collapsed system, you can describe it using a Jeans equation, where here the rho is the density and v is the velocity, phi is the gravitational potential, and so on. But we make assumptions that, okay, this is static, so there is no time dependence, it is isotropic, and stationary, so velocity is 0. So we can boil it down to this simple relation, this proportionality between the density as a function of distance from the center, which is related to the gravitational potential and the velocity dispersion. So the work is essentially summarized in this flow chart, where we can compute the intrinsic and extrinsic, as I already mentioned, extrinsic and lensing tensor field. So you can write this as a function, as a linear relation between the shape with this basis matrices. And then from there, you can compute the spectra of the source fields from auto and cross correlations. So auto cross correlations between lensing and intrinsic spectra. Then from there, you can compute the angular power spectra, and you construct a covariance matrix because we want to do like a Fisher matrix analysis and also compute the signal to noise ratio, for which we need the covariance matrix. So the covariance matrix has all these correlations and auto and cross correlations between the lensing and the intrinsic spectra. So eventually we get
3 minutes, Basundhara.
Yeah, okay.
Thanks.
So so this is the signal to noise ratio. It's given in terms of the covariance matrix, and S is the noiseless signal. So when we are taking noise to be 0, we have this matrix S. So to answer the first question that I posed earlier, that what we can know about shape and size correlations of galaxies due to these phenomena. So this is one of the main results that will summarize what we found, is that if you have an autocorrelation between shape, like this green line, so gamma stands for the intrinsic shape, gamma stands for the shear and S for the intrinsic shape. So, epsilon for the intrinsic shape or ellipticity, and S is for the intrinsic size, kappa is for the convergence, which is due to lensing. So we see that we have better cumulative signal to noise ratio in case of shape estimation compared to the size estimation. And if you combine them or cross correlate them, it doesn't help you much. So we are quite better off with the shape information itself. We don't really need to go into size estimation much. It's enough for our purpose. And the other question, if we want to extend it to flexions, we see that actually the cross correlations where lensing flexions are involved, we get a better signal to noise ratio. And for autocorrelation between flexions, it is not really useful. So flexion signal is actually about 1/10 of shape size signal. So it's already quite low. If you want to get some flexion signal, it's better you cross correlate with lensing flexions. And then if you, then only for Euclid-like surveys, we could get some optimistic results. And so, yeah, that's the conclusion. So firstly, the motivation was why we should study intrinsic alignments, because they are contaminants to the weak lensing signals, which are important on their own accord. So we cannot really avoid additional contaminants. We saw that shape size correlations are highly degenerate. So size correlations are becoming redundant in comparison to the stronger and more sensitive shape correlations. And only in optimistic cases, when we measure the intrinsic flexion with Euclid, we could specifically measure them if we look at them in cross correlation with lensing flexions. Yeah, that's all.
Thank you, Basundhara. Thanks for keeping on time. Are there any questions for Basundhara? Prabhati, I can see you have raised your hand. Please go ahead. Let me unmute you. Yeah.
Okay, thanks. Hi, Basundhara.
Hello.
So I wanted to know if your calculations are without any noise. You have not taken into account instrumental noise, right? This is a theoretical study, is it?
Yes, yes. This is purely analytical. There is no data involved. So the noise we have taken in the covariance matrices, those are essentially like short noise and noise and stuff.
Okay, so in a realistic scenario, how good will your calculations be? I mean,
Yeah, we haven't checked that.
how will your results? Okay, you haven't studied that.
No, we haven't really used. It's kind of forecast for Euclid, and so we haven't checked for existing data or surveys.
Okay, thanks.
Hello. So you said due to weak lensing, the shape and size of the galaxy will change. But how do we know in the first place that this is not the actual shape and size and it is modified due to weak lensing?
So practically, you can never observe the actual shape and size because whatever photons are coming to, they are bound to get deflected, and weak lensing is bound to happen to a certain magnitude. We cannot avoid it because it's not vacuum between you and the source, right? There is always some matter distribution, and just simply due to the the curving of space-time, this is going to happen. So weak lensing is a very powerful probe, and also it's a very significant relativistic contribution when we compute number counts of galaxies. So you have to take it into consideration. So we never can actually observe what is actually there. Yeah.
Okay, thanks.
Yeah, thanks, Prabhati. Maybe the next speaker can set up until we take another last question. I don't see any in the online room. Okay, great. Yeah. So Basundhara, thanks for the talk. I may contact you on Slack for more questions. Thanks. Okay. Our next speaker
I
have a question.
is Gopika K.
You have said that for the lensing, with lensing, they are only the tangential distortion, but for the intrinsic there will be radial. So why only?
Shall I share my screen?
Yeah, you can.
Sorry, but there's a question. I would just answer this.
Oh, sure. Yeah, go ahead. Sorry, I can't see this room anymore.
Yeah. So tangential and radial. Yeah, I'm trying to. So it depends on because the kind of tidal gravitational field that is exerted on the galaxies that are in the vicinity of the dark matter distribution, it undergoes a different kind of distortion than the one due to lensing. But okay, physically I cannot really understand explain it right now, but I'll try to find it out. Yeah.
Thank you, Basundhara. So maybe we can move on. Gopika, you can share your screen now. I have enabled it.
Yeah, thank you. I can do
Yeah.
that.
Okay, great. So the next talk will be by Gopika. She will tell us about the test of constancy of dark matter halo surface density and the radial acceleration relation in galaxy groups. I'll give a warning at about 3 minutes before time.
Okay, thank you. So I'm audible, I believe.
Yes, we can hear you.
Yes, thank you. I'm Gopika and I'm a PhD student from Indian Institute of Technology, Hyderabad. So here I shall be discussing my work, a test of constant dark matter halo surface density and radial acceleration relation in galaxy groups. So now coming first, I shall be just defining this quantity, the dark matter surface density. So several dark matter halos of galaxies and clusters, they show core profiles which are not in agreement with simulations assuming core dark matter, and has many groups. They fitted these core dark matter halo densities with a core profiles such as Berkeley profiles, isothermal profiles, etc. So you can derive these quantities rho c and rc, which are the scale parameters for these core profile, whichever core profile you're using. So an interesting observational probe was derived by several groups who had tried to fit this dark matter halo density with core profiles, and they coined this particular quantity as the dark matter surface density, which is the product of the core density and the core radius. They said that this particular quantity is constant and it is universal, like for a wide range of galaxies, irrespective of the mass, spectral type, etc. So here is the scaling relations observed for halo surface densities in galaxies. So they found that this halo surface density is about 1.9, and which is a constant in case of galaxies. But this universality of dark matter surface density were disputed in a number of works by Del Popelo et al. And etc. So now coming to this particular relation of a constant dark matter halo surface density, it is very interesting because this can be used as an acid test of alternate dark matter models. So Linen, Loeb, and Bodarengo demonstrated that the scaling relation is consistent with self-interacting dark matter, and they can be used to place constraints on dark matter self-interactions. And similarly, Burkett in 2020 work used observations of constant halo surface density to rule out fuzzy dark matter model. Similarly, this particular constancy was used by Hayashi and Shiva in 2015 work to put a lower limit to the warm dark matter particle mass. So, and also this particular scaling relation is in agreement with the Mohn prediction, given rho naught or r naught is approximately in the scale acceleration by 2 pi g. So this is a very good, this particular relations are very good for can be used as acid tests for alternate models of dark matter. So this was one of the motivation why we were urged to test this particular relation in galaxy groups. And here these dark matter scaling relations, in these are some of the results for galaxy clusters. But what we found in case of galaxy clusters from literature was that this particular quantity is an order of magnitude greater than that was found for single galaxies. So we have also one work in which in our work with cluster data, where we got this particular quantity, rho c is proportional to rc raised to minus 1.08, and this surface density, which is the product of these rho c and rc, was found to be an order of magnitude greater than that was found by for single galaxies by this previous work. So it kind of refutes that this particular quantity is constant and it is universal. So generally we were peculiar that we have to test it in a intermediate mass range between that of single galaxies and clusters. Hence this work was motivated by the same. Okay, so the galaxy groups are less massive gravitationally bound systems compared to galaxy clusters with intra-group temperature less than 2 kiloelectrovolt and typical size of 1 to 2 solar mass. They have typical mass of 10 per 13 solar mass, and they fall in the mass profile in between that of groups and single galaxies. And now coming to the galaxy group data which we analyzed, we have taken the Pointer Chandra XMM observations of 17 nearby relaxed groups, and which was extensively studied by Gastadello et al. And Sabacosta et al. So the temperature of these groups span from 1 to 3 kiloelectrovolt, and the masses from 10 per 13 to 10 per 14 solar mass. So these groups were very well studied by these groups, Zabacosta et al. And Gastadello et al. So we have this projected three-dimensional models of gas density and temperature available, and which we have used in this analysis to derive the total gravitating mass of the groups by assuming hydrostatic equilibrium. So in here we are having this relaxed group, so that assumption is kind of valid. So once we have the total mass, we are deriving the dark matter mass by subtracting the baryon content. In here, we consider the gas mass and the BCG mass as the baryon content. And the gas mass is simply obtained by integrating the gas density. And the BCG mass is determined with the assumption that m by Lk is equal to 1. So once we are having the dark matter mass, you can derive the dark matter density by taking the derivative of the dark matter mass with respect to r by 1 by times 1 by 4 pi r square. So now we are having the dark matter density for the halos uh, for 17 relapsed galaxies. So now once we have this, we can estimate the core density and the core radius by fitting this dark matter density profile by a Berke profile. In this work, we have done it using a Berke profile. So now that we can derive the core density and the core radius by these fits. So these are the core radius and the core density for the galaxy group sample. The core density is in the units of solar mass per parsec square, and the core radius is in the units of kiloparsecs. So now here is a plot which is showing the dark matter core density versus the core radius in the log space. So these red data points are for the galaxy groups data, and we have done a linear regression over here by maximizing this log likelihood function by using a EMC sampler with uniform pairs. And we have also considered this intrinsic scatter as a free parameter in this case. So these are the best fit results for the linear regression done for this ρc and between ρc versus RC and in the log space. And the slope which we are getting is minus 1.352 with an intrinsic scatter of about 27%. So we are getting a negative slope, and which is about 2 sigma away from constancy, and it is kind of agreeing with what we were getting for in case of previous results with cluster data. So now coming to dark matter surface density versus M. So here is a plot which is showing the dark matter surface density, which is the product of core density and core radius versus the M2 mass M200. So M200 we have taken as a proxy of mass. So in this particular analysis, we have considered both the group data which we have used in this particular work, as well as the cluster data we were having from Chandra cluster data. Because in order to increase the range of mass, so we have so you can see a slight positive correlation in this particular case for the dark matter surface density. So, and again, you can observe that this cluster data is falling just above that of the group data. So what we have observed and as from previous results also, this dark matter surface density is not a constant as claimed before, but it actually has a slight positive correlation with mass. And especially the cluster data is about an order of magnitude that is 10 times greater than that of the results obtained for single galaxies, and the group data is falling in between that of this value of that of single galaxies and the cluster data, and it is 4 times larger than that of single galaxies. Now,
3 minutes.
Yes. Okay. Sorry. Yeah. So now coming to this surface density is a quantity which is very model dependent. That is, you can't. This is only valid in case of code profiles. But when you will be, not all dark matter halos are of code profile, so we have to have some more universal quantity. So this is another quantity which is typically defined in literature as the column density of dark matter. So for a completeness, we have also determined the column density and plotted the column density against M200. So again, we are getting a positive correlation here for this column density of dark matter. So basically, this particular quantity is not universal, and it is having a variation with mass. Now, these are some other scaling relations, which is the dark matter surface density with K luminosity, which is claimed to be a constant in previous versus single galaxy, but we are having a slightly negative correlation, albeit with a definite scatter. And then here on the right hand side is the core radius with the K luminosity, and we can see a slight positive correlation, which is agreeing with what was seen for single galaxies in Cormanian Freeman. Now, this is a summary of the scaling relations, which I have shown earlier. The surface density versus mass is showing a positive correlation with an intrinsic scatter of 35.5%, and the surface density with luminosity, K luminosity, a negative correlation of minus 0.08, and the core radius with luminosity, that is showing a 0.71 slow positive correlation, which is agreeing with the previous results of single galaxies. And the bucket, the column density versus the mass correlation is a positive correlation of 0.13 with a intrinsic scatter of 24.8%. Now, coming to the radial acceleration relation, here is a plot showing the total acceleration versus the baryon acceleration. So this, from the spark data, this is the scaling relation between the A total and the A baryon, which is called, coined the term the radial acceleration relation. So we have tested for the radial acceleration relation in the sample of galaxy groups. So this is the plot which is showing the slope and intercepts of this A baryon, A total versus A baryon. So there is this table which is giving you a comparison of this relation, this RAR relation for our sample work as well as for other cluster previous cluster works with cluster data. So we are getting a slope of 0.36 with an intrinsic scatter of 0.42%, and the residual scatter we are getting is 0.32, which is about 3 times more than that of in cases of galaxies as well as clusters. So actually RAR is ruled out in this particular data set. And
can you wrap?
Yes, this is this is the last thing. So now I will just wrap it up. We have implemented test of constancy of dark matter in halo density as well as column density and area for this galaxy group sample. And we found that this surface density falls just below the clusters and is about 4 times larger than for isolated galaxy systems. And similarly, the accelerations, this RAR is not valid in this case, is ruled out in this case. And also the acceleration scale which we obtained is between that was seen for clusters and single galaxies. Okay, thank you.
Thank you so much, Gopika. Maybe we have time for one question.
There is a question from the room.
Yeah, please go ahead.
Okay, hi. So the dark matter density and dark matter mass, the calculation which you are considering. So why don't we consider the relative case, like use the equation?
I couldn't hear you.
I will ask someone to repeat the question from the volunteers.
Can you please say it again?
So I was asking that why don't we consider the relativistic equation of states for calculating the dark matter density, dark matter mass?
So the question is, why aren't you using relativistic equations to calculate the dark matter mass?
Okay, so this was a observational analysis. So we were like basically, maybe we will consider it later, but now we were not considering the relativistic equation, but basically trying to find, you know, a correlation between this observational probe and like how this code profiles, if whether there is any change in like while we are considering this code profiles and the NFW profiles, etc.
Okay. Thank you, Gopika. Maybe some of this rest of the discussion can be carried over on Slack.
Yes.
Can we get the next speaker, Shikhar Mittal?
Can you share your screen?
So I suppose Shikhar is in the room.
Yeah.
Yeah, thanks. So Shikhar will talk to us about background of radio photons from primordial black holes. I'll give a warning 3 minutes before. Shikhar, please.
Yeah. So hi everyone, I'll be talking about my work on the background of radio photons from primordial black holes. So I'll first start by giving a motivation for this work. So I'm sure many of you will have heard about the edges measurement of the 21 centimeter signal in 2018, which was found to contain an absorption feature, which was quite strong as compared to what the standard models would predict. In this diagram, the red curve shows the standard prediction, and the black dash line is the edges measurement. So clearly, you can see there is a huge mismatch between the two observation and the theory. So one of the potential explanation of this discrepancy is to include an excess radio background. So the measurement of the 21 centimeter signal is given by this expression, in where the XHI is a neutral hydrogen fraction and TR is the total background. So in standard calculations, we take this to be just the CMB. But if there were an excess radio background, this TR would increase and that would make delta TB more negative, and which is how we can explain this large depth. And with this excess radio background, the signal now is shown by the blue solid line, and clearly there is a reasonable agreement between the observation and theory. So now let me explain what this excess radio background is about. So this in turn is motivated by another experiment, so which is first observed by RK2 in 2011 and then later independently confirmed by LWF in 2018. So this figure that you see is the sky spectrum, where I'm showing the intensities in units of temperature, which is quite often we do in radio astronomy, where we are dealing with long wavelengths. So we can use the Rayleigh limit. So the intensity, the specific intensity J, can be expressed as in terms of temperature. So the CMB would just be a constant, the horizontal line, T gamma over here, which is about 2.73 Kelvin, which is of course a constant at all frequencies since it is of thermal origin. But the excess radio background that we are talking about is shown by the dotted line, and it is highly non-thermal, and it is given by a power law. The sum of these two temperatures is the quantity of our interest, and about 5% of this excess temperature can explain the anomalous depth in the edges measurement of the 21 centimeter signal. So because the origin of this radio background is unknown, naturally there have been several mechanisms proposed in literature, and I have shown some of them are listed over here, which is not an exhaustive list, of course, but for example, axion particles annihilating and converting into standard photons, or dark photons resonantly converting into standard model photons can explain this excess radio background, and many more other mechanisms are there. In this work, I have considered radiation from the primordial black holes. So I'll be considering two types of primordial black holes. First are the evaporating ones, and the other is the accreting primordial black hole. So let us first understand. Okay, so before I go to the details, I'll just give a motivation why I considered primordial black holes. So primordial black holes are very interesting dark matter candidates, and they have been studied in literature for about 5 decades now. And ever since Hawking had proposed that the black holes are not really black and they emit radiation. Typically we put constraints on black hole in terms of this parameter FPBH, which is basically the density of the primordial black holes related to dark matter. So this parameter being 0 implies that primordial black holes do not exist, and the one being that all of the dark matter is in the form of primordial black holes. Note that the primordial black holes are different from the astrophysical black holes in the sense that they have formed before cosmic dawn and not by the Chandrasekhar mechanism that was. So it is basically collapse of the overdense regions. So this figure that you see over here is a consolidated plot of the many constraints that have been put on the primordial black holes in terms of FPVH. So the y-axis is the FPVH in log scale, and on the x-axis we have the mass of the primordial black hole. But using the HS 21 centimeter signal in my previous work, I had put constraints, and I had found that the constraints are significantly stronger as compared to other constraints, in the sense that the shaded region shows the ruled out values of FPVH. As you can clearly see that the bottom line, that is the red solid line, is the constraint from our work, and it rules out all other previous values. But now let us come back to the first case, which is the evaporating primordial black holes. So this radiation that I am going to talk about is the Hawking radiation. I'll not go into the mechanism of it, but there are some important points to remember. Firstly, that the total energy loss rate goes as the 1 by m square, where m is the mass of the black hole. So if I consider very low mass black hole, the evaporation rate is high, and they would have evaporated before we can observe them today. On the other hand, if I consider very heavy masses, then the emission would be very low and they cannot be detected at all. So this interesting black hole masses come down to a very small range of masses, which is 10 to the 15 to 10 to the 17. The figure that you see shows a typical example of the spectrum of the Hawking radiation, and you can clearly see there is a resemblance with the black body radiation. So just one point that will be important for our discussion is that the peak of the emission of this spectrum is for example, for a 10 to the 17 gram, the peak occurs at 100 kilo electron volt. But clearly we can see that the peak of this energy is quite far from the energies of our interest, because we are interested in radio energies, which are of the order of micro electron volts. So we are going to expect very small numbers from evaporating primordial black holes. But let us now look at our results in a more quantitative fashion. So this figure will show the specific intensity that I want to calculate. And on the x-axis, I have the energy in micro electron volts. So the gray shaded band is the frequency band in which the RK and LWA made their observation. One typical example is shown of the 21 centimeter energy. Also on the secondary y-axis, there is a comparison with the specific intensity of the CMB at a typical radio photon frequency, and clearly you can see that the numbers are too small. So the curve that I'm showing is the the specific intensity for the black hole of mass 10 to the 17 gram, for which I had mentioned that the peak is approximately at 1 mega electron volt, and the energies, the values that we are interested in are in this region, where the specific intensity in SI units is about 10 to the minus 33. Clearly, this is too small, and we are immediately led to the conclusion that the evaporating primordial black holes cannot explain the excess radio background. So let us now look at a different scenario, which is the accreting primordial black holes. So this figure is just an artistic impression showing a supermassive black hole sitting and accreting matter around it and giving off strong electromagnetic radiation. So typically they are of the masses of the order of 10 to the 8 solar mass. So the idea is very simple. We are going to construct the specific intensity from the emissivity, which is this epsilon over here, and we calculate this using the specific luminosity from a single black hole times the number density of these black holes, and the the specific luminosity from a single black hole can be constructed using what are known as the fundamental plane of black hole activity. This is because usually we are not very clear about the mechanism of these jets, but so empirical relations are used, and so there are some uncertain parameters over here which I have labeled as F duty and lambda, where F duty is the duty ratio, giving us the probability for the black hole to be effectively accreting at a particular time, and lambda is the Eddington ratio. So what is interesting about this power law index is that the most probable mechanism, which is thought to be the synchrotron emission mechanism, it gives rise to a power law index of minus 0.6. What is interesting about this index is that if you convert this in terms of the temperature units using the Rayleigh's approximation, you get this index to be minus 2.6, and this is same as the index seen by the Arcade and LWA. And this makes these accreting primordial black holes quite interesting in explaining the origin of the excess radio background. So now we
2.5 minutes.
Okay, thanks. So we'll now see the results. On the y-axis, I have the temperature. This time I'm showing in terms of temperature directly. On the x-axis, we have the energy, again in microelectron volts. So for the first result, I have shown the 5% limit of the excess radio background. Why 5%? I'll just remind this because it is about 5% of this excess radio background that explains the 21 centimeter signal made observed by the edges collaboration. So the our result is shown by the solid line, and clearly because the slope is matched very well, you can clearly see that the slope is matching, and even the magnitude can be explained by a certain combination of the three parameters that are available to us, which is basically lambda and F duty. But leaving aside the edges measurement, we can even explain the full Arcade and LWA element, which is shown by the blue dotted line, and our result are shown by the solid blue line. By adjusting some parameters, we can explain the magnitude, and clearly the slope is already matched. So this makes the accreting primordial black holes very interesting in order to explain the excess radio background. So now I'll just conclude. So we have seen two types of primordial black holes in order to explain the excess radio background, but evaporating ones cannot explain this as they have very low radio emission. On the other hand, accreting primordial black holes have very strong radio emission, and they not only explain the magnitude but also explain the slope very well. Leaving aside this excess radio background, we have seen that inclusion of this excess radio background explains the strong absorption depth in the edges measurement of the 21 centimeter signal. So that is all that I have to say. Thanks.
Thank you, Shikhar. So are there questions in the room or online? I see one online, Shikhar Mittal. I'm going to unmute you. Please go ahead. Shamik?
There is one question on here.
Yeah, please take the offline question first.
Okay. So probably you might.
Hello.
Just a moment, Shamik. Let's get the offline question first.
Okay.
Okay, fine.
So you might know that there are recent estimates by Surhud group, which basically describes the edges result, or something like that. So I wanted to know if you consider those results, then how your conclusions will be modified, or will it be modified?
Basically, Sarah says that there is no absorption depth seen in the edges collaboration. So clearly, we do not need the excess radio background. Then there is no need for this stuff. Yeah, but excess radio background is there. That is independent of the edges 21 centimeter signal. So this is an independent observation.
So if you include this, there is no need of excess radio background.
Yeah, for 21 centimeter signal, we do not need to include this excess radio background. But as I have said, that Arcade and LWA are completely different observations, and they are there. So they have been well established, but the origin is not known.
Okay, so the other thing I want to know that, as you have mentioned, that the origin is not known, and you have shown that different models are trying to describe the radio background. So, is there any observational way to distinguish between these models?
No, I'm not aware.
Thanks.
Shamik, I'm going to request you to ask your question on Slack because there will be a GB meeting in 70 at like 5:45, right? So can we get the next speaker and thank Shikhar again? The next speaker is Susmita Jana. Is she in the room?
Yes, she is.
Yeah, correct.
Share.
Okay. Yeah. So Susmita will talk about constraints on the non-minimal coupling of electromagnetic field from astrophysical observations.
So we can use this.
Yeah, you can start, Susmita.
Hello.
Yeah, we can hear you. Go ahead.
Good evening, everyone. So today I'll be talking about my recent work on constraints on the non-minimal coupling of electromagnetic fields from astrophysical observations. And this work has been done in collaboration with my supervisor, Professor Shikhar Mittal. This work has been archived, so if anyone is interested, can have a look. So first, let me give the motivations behind this work. So we all know that electromagnetic waves are hello.
Yeah, I think it will not come, so you have to speak a little louder.
Okay. Sorry. Is it all right now? Oh, thank you. So let me give the motivations first. So we know that electromagnetic waves have always been integral part of astrophysical observations. So in order to test general relativity or other alternative theories of gravity, it's important to study electromagnetic fields in presence of gravity or in curved spacetime. To do so, usually we consider a general spacetime metric in curved spacetime and change the partial derivative into covariant derivative in order to study the dynamics of electromagnetic fields in presence of gravity. And these theories, I mean the predictions from these theories has been tested in high accuracy in big gravitational region, but not has been verified well in strong gravitational regions. And since we don't have a very good understanding about gravitational attraction in strong gravitational regions, such as near a black hole or other compact objects. So in that case, to study the gravitational attraction in strong regime, we can use electromagnetic fields or electromagnetic waves. We can use them as a tool in order to probe gravity in such regions. So to proceed further in that way, we can consider non-minimal coupling instead of minimal coupling. Minimal coupling means where we consider the curved spacetime metric instead of Euclidean metric, and non-minimal coupling is where we include minimal coupling as well as the interaction of Maxwell's tensor. Interaction of Maxwell's tensor with the curvature tensor or its dual, and these interactions become very relevant in strong gravitational region because in strong gravitational region we have higher curvature tensor, and in such regions these type of interactions become more important rather than the minimal coupling. So here I have shown one general model for non-minimal coupling. In question 1, you can see that the first two terms represents the minimal coupling, and the last term represents the non-minimal coupling of electromagnetic fields with the curvature tensor of the spacetime. And this chi includes all the curvature tensors such as Ricci tensor and Ricci scalar and Riemann curvature tensor. And this model is quite complicated, so there a simpler model can be considered by choosing these Q1 and Q2 to be 0, and these this equation 3 can be, this the action 3 can be obtained. And this model, the simpler model was proposed by Prasanna in 1971. Both of these models are invariant under CPT and general coordinate transformation. However, both of them violates Einstein's equivalence principle. So one thing I should mention that these models, I mean, studying non-minimal coupling of electromagnetic fields is valid for the electromagnetic waves of very high energy. And I can say specifically that the electromagnetic waves have to have energy of order hard X-rays. Low energy lower than hard X-rays. I mean, the electromagnetic fields having energy lower than hard X-rays can be studied in a different manner. And those models, I mean, some other people have worked on those other models. However, I haven't shown their work here because of the constraint on the time. But I just thought that it is important to mention that these type of analysis can be done in different manner, taking into account the energy level that we are interested in. So from here, I will consider the simpler model, and from that we can obtain this equation motion 4, and using the symmetries and Bianchi identity related to Riemann curvature tensor, we can obtain this equation 5. And the two terms in the right hand side can be interpreted as the kinetic term and the mass term. And here, as we will study this equation of motions near a black hole, and the equation of motion depends on the type of black hole also. For instance, for a static black hole, where the Ricci tensor is proportional to metric tensor, the second term that includes the covariant derivative of Ricci tensor vanishes. But if we consider a time-dependent black hole, where the Ricci tensor is not directly proportional to the metric tensor, this term retains. So in the next slide, I have shown the possibilities that can be explored from this work. So here in the left hand side, I have shown a picture that shows that there is a black hole and there is a bunch of photons coming from very far distance, and they are getting deflected because of the gravitational attraction of the black hole. And as you can see that there are two types of deflections occurring here, and the different deflections we are seeing depending on the mode of polarization of the photons. Okay, so that we have worked here also, and we have derived the deflection angles that depend on the mode of polarization of the photon. So first, we can derive the dispersion relation for the photon, and that will be very different to the usual dispersion relation, p square equal to 0. And from that, we can calculate the polarization dependent deflection angle, or even the time of arrival of the photons can be obtained also. And from that, what we have done, we have calculated the constraint, that is a constraint on the coupling constant that was present in the model that I mentioned before. To proceed further, we need to consider a particular type of black hole. So here I have considered two types of black holes. For the first one, we have considered the Schwarzschild black hole, and the second one I have considered the Sultana-Dyer black hole, and Sultana-Dyer black hole is a time-dependent black hole. But we have found that the constraints on the coupling parameter strongly depends on the type of black hole. I mean, it depends on the time independent or time dependentness of the black hole. Now here I have shown the length element in Sultana-Dyer metric. So you can see that I mean, here this eta represents the conformal time, and this eta 0 represents the conformal time at current cosmic time. So this metric is very similar to Schwarzschild black hole. Even the Sultana-Dyer black hole has the same null geodesic, the same horizon radius, and same ISO and etc. Exactly equal to the Schwarzschild black hole. And Sultana-Dyer metric can be interpreted as a Schwarzschild black hole that is embedded in the matter-dominated expanding universe. And in one sentence, I can say that Sultana-Dyer black hole is a cosmological black hole that is very similar to a Schwarzschild black hole, just embedded in the expanding in the background expanding universe. So
3 minutes.
okay. So to proceed further, I have broken the methodology into 3 steps. First, I have obtained the modified dispersion relation in a local inertial frame. Then I have rewritten all those relations in the real non-local frame, non-local non-inertial frame. Then I obtained the physical quantities. Here I am skipping first 2 steps and I'm just going into the physical quantities that I have obtained. So these are the deflection angles. I mean the difference between the deflection angles for plus and minus polarization, considering Schwarzschild and Sultana-Dyer black hole, and both these quantities has been obtained at a particular radius that is r equal to 3/2 into horizon radius. Actually, this is the radius of photon sphere. Here, this parameter b is important, and it is related. I mean, it can be interpreted as the inverse of impact parameter. However, it is not exactly equal to the inverse of impact parameter, because for the Sultana-Dyer black hole, we have considered conformal time, and the conserved quantity cannot be the conserved quantity is not exactly same to the energy. So anyway, the result will depend on this parameter b. That's why I mentioned it here. And here this beta 0 is a dimensionless quantity. It depends on these natural constants, and this alpha has a dimension of length. Now, using these results, I have obtained this constraint on the lambda for the Sultana-Dyer solar mass black hole. This constraint on the lambda for Schwarzschild black hole was obtained by Prasanna in 2003, and that is of order 10 to the power 20 centimeters square. And for the Sultana-Dyer black hole, I have obtained the constraint to be of 10 to the power 10 centimeters square for the solar mass black hole. Now here I have shown the difference between the deflection angles for a solar mass black hole. I mean for the Schwarzschild and Sultana-Dyer black hole. This blue line is for Sultana-Dyer and the red line is for Schwarzschild. So you can see that the behavior of the curves depend on the value of b. For the higher value of b, I mean when the impact parameter is low, the value of the deflection angle, I mean the difference between the deflection angles for Sultana-Dyer is lesser than the Schwarzschild one. But when the value of b is low, that means the impact parameter is higher, then the value for the Sultana-Dyer black hole is higher than the Schwarzschild. So from this behavior, I mean this behavior is important because if if we can verify this work from observational data, and if we get a familiar behavior, then that will be very, very helpful to understand the gravitational attraction of a black hole. I mean, from these results, we can interpret the behavior of the black hole. I mean, whether the black hole we should interpret the black hole as a dynamical object or a static object. Now, in the next slide,
to wrap up.
Yes, I just need 10 seconds. Yeah. Now here I have shown the same behavior for a different mass of black hole, and it gives exactly the same behavior as the previous one, as the solar mass black hole.
So now just I want to mention that this work can be, I mean, this work is entirely an analytical work. There is no observational evidence yet. But anyway, we can aim for it, and there are some futuristic high frequency X-ray telescopes that the people can look into, and we hope that from those data we can confirm or inform the existence of the non-minimum coupling. Thank you.
Yes, Susmita.
There is an offline question, sir.
Yep. Please go ahead with the offline question.
So you said that you have put some constant on lambda, but you have not used any observational data. So how did you get the constant from?
Yes. Okay. So from this expression, you can see that there is a root over of this quantity, and this quantity has to be positive. This 3 to the power 6 minus 16 into lambda tilde. So from this constraint, this has to be either equal to or greater than 0. And from that constraint, I have obtained the value.
Is it a constant, or is it just okay? Your theory is valid for these values.
No, it's a constraint. And for the Schwarzschild case also, I mean, in a similar fashion, the constraint has been obtained.
Okay.
Yes, yes.
Okay, so you said previously also there were some different constants, which was like order 20. So, like, how they're different then? Like, what? Because you are also using Schwarzschild, they are also using Schwarzschild.
Yes, for Schwarzschild, this is the value, but for Sultana Dyer black hole, this is for a case for the Sultana Dyer black hole. I am getting the different value that is of order 10 per 10.
Okay, this is
the black holes are different.
Okay. Any other questions?
So offline there is no more questions.
Okay, I also don't see any questions online. So this brings us to the conclusion of the first session. Let's thank all the speakers once again. The general body meeting will begin in 5 minutes, and the second session will be tomorrow. So we'll see you there. Thank you so much. Thanks a lot.
Thank you so much.
There is no. Oh, so it's in 5.